So I guess yeah. So we'll start now. So last class we talked about assignment one, and also we talked about neural networks in general, and we saw that uh, where's this? Zoom this a little bit, and yeah. So we saw that how a typical neural network works, and how all these layers work together to uh, yes. So how all these layers work together to give us outputs, and we talked about all these functions representing it as a linear combination of weights and biases, and then we sort of tried to add some non-linearity to it. And after so we talked about different kind of non-linearities that is there in the literature, that is softmax, and that is tan H and all those things. And then we briefly talked about gradient descent, and then we talked about how gradient descent is used to learn all these weights, and sort of try to find the best parameters which approximate these functions um, perfectly or almost perfectly. So we talked about all these things in the last class. Do you guys have any doubt in the last class as such till now? Open the chat. Okay, so there is no doubt, I guess, in the last class. I think Sun said when run lecture 15 program showing error message. Okay. Uh, I guess in this live lectures, we're not supposed to run the codes. If there is error, you can just skip that part and go ahead with the other parts. But yeah, I guess we're not supposed to do. But let me see like what is there in the curriculum. So we have covered till this. So week zero content, everything is done. Week one is done almost. We talked about all the classification models and perception models, and so this is done. So week five lecture has been uploaded. So we should be covering till week four. So introduction to deep learning with neural network. This I have covered. Introduction to deep learning with neural networks again. Introduction to perception and deep neural networks. I guess this is also covered in this thing. And multi-layer perception and deep neural network. Classification with multi-layer perception, and lecture materials. So I guess week two content is almost like done. So if you guys have watched till week two, let me know what is the doubt in week two. Like ask the doubt in a specific format so that it can be answered. Like don't ask doubt so that like re-explain everything in the week two. So that will be like too big to explain. So I'll just give you 5 minutes. If you have to go through your notes or something, just go through them and try to see what you don't understand, and let me know if you don't understand anything. So I'll try to clarify that. So okay, so I guess autoencoders that has been taught in week three. So till week two, I guess everyone has a clear yeah. I guess everyone has clear understanding till week two. So normal introduction to deep learning has been covered. So could you guys let me know like where does this programming starts, like after which week? Is there any programming assignment in week two? Hello, are you guys present? Can someone say like is there any if there is any doubt or any programming session in week two that we can recover? Okay. So yes, no one is replying, but I'll assume that week two assignments are clear. But for the sake of completeness, I will discuss the assignment of week number two. Uh, okay, so let's not discuss week number two assignment. Let's just go. Let's just come to week number three because someone just asked about something about lecture 15. So what we can so what we will do is that okay. So someone asked about week two question. Uh, for one single scalar multiplication of x1 and w1, how much um, memory read write operation goes? Yeah, the answer is three, I guess. The answer is three given. So I will try to explain. So let me do one thing. Let me just take this to uh, mm, okay. So week number two, question number two. Uh, yeah, I guess this is different. But, let me just explain it here itself. So there is this two scalar entity x1 and w1, and so it is asking that how many memory iteration do we need? So how many memory read write operation do we need for this class scalar multiplication? The answer is okay. The answer is so you are sort of so there is x1 and there is w1. Okay, so in the memory there will be x1, and in the memory there will be somewhere w1, right? So to multiply these two scalar multiplication, first thing you need to do is that you need to read the x1 and w1 to the from the hard disk to the memory, right? So there is operation number one, reading x1, then operation number two, reading w1. So this is like two operations, two reading operation. Then you multiply it W into X1, and you get the result R. Okay. So after getting this result R, you need to again store it to some memory location here in the computer. And so this is one operation. So there is two and there is one. So total will be three. So in total, there will be three memory operations for a scalar multiplication. And this is a part of computer architecture, so we can refer that as well. Okay. So I guess we don't need to discuss anything from week two. If anyone of you have any doubts regarding that, we can discuss. But yeah, so we can go to the week three. Uh, uh, yes. So so we'll start with autoencoder. Week three, last question. So we'll just discuss about the contents of week three, and after the discussion, we'll go to the questions and solve everything. So let's start with the week three, and if everyone is agreeing with me, I can go ahead and start discussing all the week three materials. Of course, I won't be covering everything. So for everything, you need to refer to the lectures, but we can go and discuss about week three material. So I guess not everyone is covering them. So I guess I'll just cover some of the contents and then we can go to the questions. Is it all right for everyone, or is it so I just need to go to the solution? Okay. Let's just start with start this week's lecture with autoencoders. So before going there, I would like you to go. I'll try to share my YouTube channel where I'm uploading all the videos, so that one second. Okay. So I have shared the YouTube channel where I have uploaded all the videos. Uh, so I'll also share the link for the past videos. You can go here and watch. And this week's this recording will also be uploaded here. So someone is okay. So we'll start with autoencoders. So are there anyone like who is like uh, understood autoencoders completely? Hello. Are any of you guys are like have understood the autoencoders completely? So based on the response, I will go into the depth or I will skip some of the things if I like. So if you are comfortable with that, like I'll go very superficially and directly go and solve the questions. But if you need much more explanation, I can give. Okay. So I'll just start with the thing like before asking anyone. Okay. So while discussing autoencoder, the first thing is that autoencoder is a very simple and very fundamental architecture that is used for representation learning. So first thing is representation learning. First thing is representation learning, and second is denoising also, and third is compressing. So these are like the use cases of autoencoders. So first I will go through the architecture and how the training happens. Then we can see how it is working in general. Okay. So let's say I have a let's say I have a digit image. Okay. So it is like image of 7, and so there is the image which is 0, and there is the image which is 1. Okay. So if you look into these images, in 7, only these pixels are black and others are white. And in 0, only these pixels are black, others are white. So if I look into it, I can say that the number of pixels that are used to store this 7 is much more less than the entire image, right? Like if the image is 7, I can just store it using all these pixels. And if you see these two images, the number of pixels that are common between these two images are very high. Like if you see, all these pixels are similar in all the images, right? All these pixels also, the value is same, right? So what if I can represent the same amount of information in smaller bits? Okay, because if this is a 28 cross 28 black and white image, uh, the amount of bit we need to store each pixel, let's say 8, then total number will be 28 plus 28 plus 28. So 28 plus 28 plus 8. So we need this much amount of bits to store the image. But if we represent this 28 plus 28 image into a 100 dimensional image, then total number of bits will be 100 into 8. So I guess here we have reduced the bits required to represent the same image by a factor of 7 or 8. Okay. So we wanted a tool where, like, first thing is that we saw that all the images have like there is some main content on top of it, like 7, 0, and 1, and there are some useless content. So useless content and content, as I mean, there are some background images or there are some background information which doesn't require and which is same across all the images, and which doesn't require um, many memory location to be stored. We can say that we can store all those background information in one place, and and all the main information in another place. What we can do is that we can take every time we go for see the image, we can just take the background information from this place and the main content from this place, and just merge it somehow and get. So motivation number one is that we need to so there are useless bits around the images. Second motivation is that we need lesser space to store the image, and for that we need to find a way to compress the same image such that it will be represented without any loss, such that it will be represented using small number of bits. So is this motivation clear as of now? Then I can go forward, like how to like go about and do this. I mean, how to go around and find the solution to this, like how to represent the same like 28 cross 28 bit thing into a 100 dimensional vector. So if this motivation is clear, let me know. I'll proceed further. Okay, so I guess uh, yeah. So we'll start with the concept of autoencoder, and yes, I was mute for some time. Okay, so here is the image. Let's see, it's image. Let's say it's the image of 7, and we are passing this to a input layer. Then the content of this input layer will be go to another layer. Then we'll go to another layer whose dimension is 100 or 100. Okay. So what we need is that. So what is this? What is the need of this layer? Like what are the conditions this layer should satisfy? First is that this layer should be uh, small. I mean, the dimension of this layer should be less than the dimension of the original data. Second thing is that this layer hello, am I audible?
Yes, yes, audible.
Okay. So yeah, I guess Swati, your mic might be problematic. So you take care of that. Okay. So this layer should be small. Second thing is that this layer should have features uh, which represent 7. Okay. So there are two requirements. One is that this should be small enough, and second is that this should represent the factors of 7. Because if we don't represent don't know how to represent 7, and then this is of no use, right? So this should be a current representation of 7. So how do we verify that this is a correct representation of 7? So what we can do is that the same network we designed here, we can just copy it in this direction like this. And so, and when we get the output here, the output will be a same 28 cross 28 image. Okay. But as we discussed neural network, so initially the number of weights that I'm putting the weights that I'm putting here in this intermediate layer will be random initially, and when we run the gradient descent, it will be optimized. So these optimization of weights ensures that the loss of the network should be minimized. So there is two terms. So first thing is that we optimize the weight, optimize the W's, uh, W's by yes, by minimizing the loss. Okay, so one term is minimizing the loss, one term is optimizing the W. Okay, so we need to so every architecture that you are going to see in deep learning, so you need to minimize the loss. So, and how to minimize the loss using gradient descent. So you have to think that gradient descent is working in the behind, and so you just need to find the loss function, and after you find the loss function, you just feed that loss function, and you just want to you just tell the gradient descent algorithm that give me optimal set of weights which will minimize this loss. So the gradient descent algorithm will find the optimal set of weights which will minimize this loss. And once the loss is minimized, your goal will be achieved. So our goal is that this d should be small enough. we can achieve that by adding a small number of neurons in the middle. And second goal is that we need features which can represent the seven. Like even if I give this 100-dimensional vector, this should contain that much amount of knowledge, such that this should contain that much amount of information which is contained by seven here. It is contained by seven here. So this much amount of information should be contained within this 100 dimension. So let me clarify. So when you have a book of say 1,000 pages, and you want to summarize the book into say 10 pages, okay, so obviously there will be a loss of information, right? So you are compressing something. So is the think it of as compressing a audio file or video file. When you compress a video file, of course you get a smaller size video file, which is small in size, but as a consequence, you also lose on the quality, right? You cannot get fully clear video file that you compressed earlier, and uh, and get better quality. You always get some lose in the always get some reduction in the quality of the video. Similarly, when you're compressing the information here, you will also lose some quality, but all the essence. But when you see a blurred video or compressed video, you can see that even if the quality, even if the video file size is much smaller than the original one, the quality decrease is not in terms of the semantics of the video. Or you can say that when you compress that video, you can always see that video clearly, like even if not very clearly, you can always see that video and understand that, okay, what this is what happening in this scene. So it doesn't lose that information for which the video is made. So it's always a compression which compresses the data, not the entire video as such, like not the visual appearance of the video. So here also we will compress this 7 into smaller dimensional vector, and also we'll try that the information that it is containing should be intact. So how to model this second thing, feature which find feature which represents 7, and sort of and sort of uh, uh, get it inside a smaller dimension. So one thing is that we need to design a loss, and the loss should be such that so what we want, this z. So let's call this z, okay. So we want this z to be sufficient enough to reproduce 7. So we want the final image also look like 7, okay. We want the final image also look like 7. So for that, the loss should be, so we want this should be similar, right? So that's why we want the distance of, let's say, this x, uh, let's call this x, and let's call this x dash, okay. And we want x, we want x to look like x dash. That means we want x to be closer to x dash. That means we want the distance between x and x dash should be small. So also, if we put it in that way, we want the distance between x1 to x should be minimized. So for this, we take a modular difference between x dash and x, and we can treat this as our loss. So anything you put as loss, that will be minimized. So if you want to do any minimization, you just put it inside the loss. And even if you do, if you found something, say f, and you want to maximize this, in the loss you just put 1 by f. So when you maximize the function, its inverse will be minimized. Or you can say if you are minimizing the inverse, minimizing a function, then its inverse will be maximized. So since we want the distance between the final image and the initial image to be minimum, We're just minimizing this. So this is this L1 distance. For L2 distance, you can just put it as x dash minus x2. So here is L1. L2 is just the mean square error between these two. So once you do this, so initially the weights will be random. Once you start training, the weights will be up. So initially weight will be random here. And when you train, it will come down to the optimal weight, but the loss will be minimum. And this set of weight will help you to given a 7. It will take this to encode it to Z, decode it to 7 again. After that, the training has been done completely. You can do this thing. Okay. So this kind of autoencoder is called vanilla autoencoder. This is a architecture of autoencoder, and these are called vanilla autoencoders. And here, this part is called encoder. This part is called decoder, and this middle part is called latent code, or you can say Z. Typically named as Z. It's called latent code, or you can say hidden layer, or hidden codes. So this thing is clear, right? So if this thing is clear, I will go and tell about what advantage do you get by creating this sort of arrangement. Can you explain MSA again? So MSA is the mean square error. So suppose so there is an image. Okay. So these are pixels. So I've explained in the first class. An image is nothing but a matrix. Okay, let's just put value 2, 3, 1, 4, 6, 7, 9, 10, 3. Suppose this is a 3 cross 3 image. So if the image is 28 cross 28, that will be 28 cross 28 matrix. And this say X. Similarly, you will have X dash, and it will also have a matrix value 1, 3, 1, 2, 3, 7, like this. So what you do is that if you take element wise subtraction, 2 minus 1 equals to 1, 3 minus 2 equals to 1, and make a matrix out of it. And similarly, fill all those values and make a matrix out of it, will be 1, 1, and all those things. So this is just element wise subtraction, right? So this is L1 loss. When you go to L2 loss, it's like x1 minus x2 whole x1 square minus x2 square whole root, something like this. Let me yeah yes. So this is not like this. X1 x2 square, taking whole square, and if you have like 10 images, so this is square error. I mean, you take the square, you take the error and square it. MSE is the mean square error. Like suppose you have 10 images, what you do is that you take all the images and xi minus sorry xi minus x dash I, and you sum it, I goes to 1 to 10, and you take average of it 1 by 10 is square. So xi will be like first xi will be first, x1 will be first image, and x2 will be second image, and x1 dash will be the its reconstructed form, and similarly x2 x2 dash, x3, x3 dash, you just take all those difference and take squares of it, add everything, and divide it by the number of samples that you are taking. So it will be, it's the MSE error. And um, so this subtraction here is 111, and you just take a square of it. Just take squares of it. Any element, you square it, you'll get the mean square error out of it. So this is the way like we do mean square error between two images. Is this thing clear? Okay. So let's go to like what. So you might be thinking, so yes, I have 7. I encoded it to, let's say, a code Z, and I encoded it in such a way that I can reconstruct again the 7, right? And and we can say that this Z is correctly representing 7. Why? Because given this Z, I can reconstruct the 7 again. So with this fact, I do convinced that like Z is a latent code, and it is dimensionally much more smaller than this 7. And with this small dimension, it can retain the information, almost all the information that is there in the 7. But you can say that what is the need, right? Like, why do we need to store a representation of the 7 if we can store 7? And what is the need of like forming the same 7 again? Because there is no magic, right? We have 7, we get the 7 again. So what are we going to do with the 7? So basically, so this is not the case. I'll let you know what is the application domain of this application domain. Applications. Suppose here is a sender, and here is a receiver. Okay, and you want to communicate and send data from sender to receiver. So if you send these images, so you need 28 cross 28 into 8 bits per image. Okay, this is one method. If you have an encoder decoder, what you can do is that if you have auto encoder, you can place the encoder here. Okay, suppose this image comes, you just find the corresponding Z here. Okay, this is sender S and this is receiver R. What you can do is that instead of sending this image, you can send this Z. Okay, and this Z will go here, and I will place the decoder here, and I'll get back the image. So in the channel, what amount of information that I sent? 100 cross 8 bits per image. So there is a significant reduction of number of bits that I need to send while sending this image. This can be also seen that when you are storing image, one can store in this fashion all the image in the memory block. Or what one can do is that one can store all the Z values. Along with that, you store the encoder and decoder. Whenever I want the corresponding image, I'll just put it inside decoder. So whenever an image comes, I'll put it inside encoder and I'll store it here. Whenever I need the image back, I'll just take the input from here, and I'll decode it and I'll get the image. So it will also reduce the storing cost of the image in a computer. So is this application of decoder clear till now? So to store information in a smaller disk size. Yes. Sumit said yes. I guess not many people are there today because Some people said me to move the timings. So I moved it to 4 to 6. And again, last class, some people said that we're happy with 6 to 8, but make it Thursday. I again requested them. They said that they cannot keep on changing times. If you want the session to be in the 6 to 8 on Thursdays, you can request them on the request portal or raise a query or something. They can go there and they can see the if they see the query, and if they accept, we can move the time to that time. Yeah. So is this thing clear? The storing thing?
Yes, sir.
I have working time from 9 to 5 p.m. Yes, everyone has a working time, I guess, but like I don't know why I said 4 to 6, because in the session, in the first session, people said that 4 to 6 will be fine. Uh, mm, might be like you can take a early leave or just attend the lectures from the office itself. Uh, Okay. So before moving to the second application of autoencoder, so I just need to, yeah. First one is compression. Second, let me write this as well. First one is compression, and second one is denoising. So denoising is that suppose we have an image of 7. Along with 7, we have some noise on it. So what we want to do? We want to find a clean 7. Okay. So this is the task. So if this is the task, what should we do to find the clean 7 given the noisy 7? So, so here should be two goals. Similarly, like first should be the representation, and second is that removal of noise. The architecture will be same. Like we have an encoder E. Like you just add some layers initially, then you will get a code Z. Then you decode it using decoder. Here it will be noisy 7 as input. So how to train this? So for training, you have to take a noisy 7 into input, and in the output, what happened? So we want clean 7, right? But initially, when the models is not trained, we'll not a clean 7, we'll just some garbage noise. So what do we want? We want to remove the noise. So let's just form this. Let's just formulate this as a minimization problem. where we want to minimize the distance. So can we guess like here what do we need to minimize? So suppose this is x and this is x dash, and suppose we have a xc, which is a clean sample of 7, like clean. There is no noise. Here there is noise, and here there is no noise, and here there is the output xc. Of course, we want x to be input to the network, and we'll get a representation z. And the output x dash, we want x dash such that it should be closer to xc, and it should not be closer to x. Okay, there is two things. It should be closer to xc, and it should not be closer to x. So the loss function, that's why will be the mean square error between x dash and xc clean. So if we minimize this, the distance between xc and x dash will decrease. At the end, when we pass a noisy image as input, in the response, we'll get a clean 7. Because since we are minimizing the distance between the reconstructed image and the original input 7, so this minimization will lead to constructing better 7 images. So this is the idea. So one real world application is that the healthcare data. So in healthcare, let's say in healthcare, we have some liver image like this, but due to the poor quality of camera, because these camera are generally put inside our mouth, and the picture is taken, so the quality might be poor. So due to this poor quality, we get some noise. So before doing any deep learning on top of it, we first denoise it, and we get a better version of the image with less noise. We cannot obviously remove every noise. We get a better version of noise, and after this, that we put it into any neural network for classification. Classification or anything. So this is the idea. So this is the motivation, and this is the purpose behind denoising autoencoders. So these are called denoising autoencoders, but the loss is between x dash and xc, not the x, because x is again noisy. So we're not interested in finding noisy images. So yeah. So till this point, everything is clear. Sumit said yes. Everyone, please respond. Uh, any algorithm used to remove this noise? Uh, so this is the algorithm, right? So okay. So let me re-clarify. So these are neural networks, and we train this using gradient descent. Okay. So this is the input to the neural network, and this is the output. So the beauty of gradient descent is that it can minimize any function that is given. We generally minimize the loss, but it can minimize any function that is given. And since it is minimizing, so initially all these weights will have yes. So initially all these weights will have random values, and after the minimization has happened, it will have optimal value. So if we give a 7 here, it will give us clean 7. So how does it give us clean 7? it will find the weights, those weights. If we multiply those weights to 7 and carry forward the multiplication, at the end it will give us the clean version of 7. And so initially it won't give because the weights are not optimized, the weights are not that good. But yeah, so after the optimization it will give me those weights, which if I have multiplied to the my current image, it will give me the final image of 7. Since it is optimized, it will give. So this optimization is done using gradient descent. So yeah, for comparison, other than gradient descent, acha. So gradient descent is not used to remove the noise. Gradient descent is used to minimize this loss. This loss that you see, MSC, XC versus XS, XS minus XC, is to minimize this. So if you're asking, is there any other algorithm that is used for minimization of loss? So actually for minimization purpose, in neural network, we use gradient descent. And for anything else, so if you're asking, is there any algorithm? Yes, there are algorithms. But since neural network is a very complex model, neural network is a very complex function in itself, it is harder to minimize it using other methods. So that's why gradient descent is the mostly used methods, or you can say the only used method in neural network. Yes, there are other methods, but because if you recall, if so, what is the method to minimize x square? Suppose fx is x square. In high school, you must have learned that to minimize something. So let's say x square plus 4, 4x plus 2. So how to minimize this function? You just take df x by dx. You will get 2x plus 4. For minimization, what you do is that uh, you take this as 0, then you type 2x equal to minus 4, x equals to minus half, sorry, x equals to minus 4 by 2 equals to minus 2. So you can say that when x equals to minus 2, this function is minimum. Okay, this function is minimum. Minus 2. Okay, so you can say x equal to this function is minimum. But here the function is much more complex than this, and this is a convex function. Okay, you can just find the minimum right away. But if you look into this neural network, these are very complex functions, and it is not generally not very feasible to find it using this method, like taking gradient and taking the first order information and finding the minimum. But for I guess for this, we are using gradient descent. So instead of taking the direct step, we are just taking small steps towards the minimum. Gradient descent is used for minimization of a function, not compression, like not denoising. Okay. Is this thing clear, Krishna Kumar? You asked this question.
Yes, sir. Thank you.
After PhD, you will go to same college.
Okay. Okay. So I am actually not aware of what other thing is. So okay. So we saw that we used autoencode for representing the same information in a smaller number of bits, and also we use this for denoising. So has anyone like can let me know what else is covered in week 3 if anyone has gone through the lectures and stuff, like what other things are discussed in autoencoders that I can discuss before going to the assignment.
Sir, while going through the lecture 12 and the subsequent lectures, I came to know that sir have taken database from MNIST and ALLIDB version 1 and 2. In MNIST, sir discussed regarding gray image, and in all IDB2, sir discussed regarding
The colorful images.
color images. and what we have discussed currently is somewhat known to me. That means I just able to recall that what sir had said in that lecture.
Okay. So I guess these lectures have programming assignments, right? Like, or programming going on in parallel, right?
Yeah. So everything sir actually interpreted with the help of Python IDE.
Okay. So do you want me to go through that, like reiterate the settings? And so if you have any doubts regarding the programming related to this, you can also ask. So this is the main idea. Did you get the main idea? You get the main idea, right? Like, we're representing it using a small set of number of neurons Z, and then we're reconstructing it.
Yes,
So
sir. No need to detail the things, but can you just give a gist of what happens during the lecture 12, 13, and 14? Because
no,
in the
like,
case
see,
of
I haven't went through the lectures because I am not taking this course, right? But if you have went through the lectures and you found something that is not you are not understanding, I can help you there. Otherwise, like, if I go through the lecture, then it will be like I am also doing the courses, right? But like, I
no,
know the
actually,
content.
yes, sir, yes, sir. So if you know the content means you just explain the content enough, sir. So we will be able to interrogate the reference to week 3 also.
Sorry, I didn't get the last point. So see, I mean, I went to the week 2 and I see these things, the multi-layer perceptor and all these things.
Yeah.
I just discussed all these things, so I cannot go through and see what the exact
Yes, sir.
thing
Actually,
there.
that is the one I also need. You just explain with the help of that lecture topic. It's enough for us to recall the things. That's all.
Okay, so the MNIST handwritten digit classification using autoencoder. So the thing I discussed here is, I guess, pull this out. The thing I discussed here. So this is for. So this is MNIST, right? So MNIST is a 7x7 image. Okay, so 28 cross 28 cross, sorry, not 7x7, 28 cross 28 image. And so using this MNIST, we sort of created that code Z. And for classification, instead of passing the entire image of 7, we are passing the representation. So using this, like, so that is the thing with classification. I will explain that. And second is fast and image classification using autoencoders. Third is all IDB classification is autoencoders. So okay, so this is detection and assignments. Okay, so I'll just try to cover this now, and then I'll just try to code this thing using PyTorch, the library. So just stay with me. We can take a now 5 minute short break, and we can reconnect after that in 5 minutes. Okay. Yeah. Hello. So, can any one of you share me the link of uh, the GitHub or the code that they used for all these things? If you have any the link for the code. The GitHub a link or any link. Okay, I got it. So we'll be looking into with 3, 8, lecture 12. So let me open the code first. Okay, so this is the code, right? Let kernel. Okay, so this is not. It's not working here. Let me do one thing. Let me download this file and run it in my local. So is this thing visible to you clearly?
Yes, visible.
So did you guys run this before? Or, okay. So the first thing is this block is loading package. So you can just load the package here and let it run first. Actually, initially I need to connect to the this thing uh, server. Then I can run this. Disconnecting to the server. Give me some time. Mm, it is taking time. So, okay, so I'll just try to point out here without running them. Once it is connected, we can connect so this is like the connection to kernel base. So it is taking time, but once it is connected, we will run the code as well. So you see these things. You see these things. So these things are called imports. If you're not familiar with PyTorch, I will just try to go through it. So you're importing certain libraries. This library torch is the PyTorch, which sort of have everything that is related to neural network. You can code everything related to neural network using PyTorch. And here this from torch.nn as nn. So this nn means neural network, and torch.optim as optim. So this optim is the optimizers, and so torch vision is another different package which have different data sets in it. So yeah. So the MNIST dataset that we are talking about, the dataset of images. So if you go to the internet and type MNIST, yeah, if you go to the internet and type MNIST, you can find these images. So the dataset is kind of this. It is a handwritten digit dataset, and where every digit is written on top of a black and white surface. And so yes, so to load the dataset, the command is pretty straightforward. You just go and go to the datasets, then .mnist, and you specify a folder where that mnist is to be downloaded if it is not already there. And when you put train equals to true, so I mentioned that there are two types of so you divide the data set into two types, two things. One is test data, the another one is test data, train data. And so this is train data, so that's why you put train equals to true. And download equals to true means that if the data set is not present locally, you're just downloading it to the local. And data path is here where the data is actually residing inside this mnist folder. So it is residing inside this raw folder. And yeah, so so this is another function. So we'll just go through it later. But yeah, these are the functions, utility functions, I guess. So these are the files to read the labels and read the sort of read the image and all these things, and printing those images and their size, their labels and all these things. So this thing is like just looking at the image and seeing what it is. And then we come to this part. I guess I should be running this, but I don't know why it is not getting run. Let me connect to somewhere and try to see if I'm able to run there. If I'm able to run there, then I guess I can run it there. Documents. Can I import and use Torch for Python installed over Windows OS? Yes, the thing you need to do is that just pip install Torch. So this will install your PyTorch package in your Windows. So I guess it is running now. We can go ahead and no modeling torch. You can go ahead and install stuffs. Okay, so this is running. Yes, are you guys here? Okay, so you guys are here. So I have imported everything, and then I'm loading the data. I'll just change the location so that it will be convenient for me. And assets and okay, it is downloading again. I don't know why. Okay. Yeah, I guess yeah. So we downloaded this data set. So and so this if you put a location in your system, it will download to your location as well. So this is downloaded. Then we're specifying the data path. I guess this data path also need to be specified again. Raw. This and all these functions need to be run. And so it is so throwing some error could not find renderer. Read image file. So we'll skip this part as well. Actually, it's just reading the image and showing. We'll go to the autoencoder part. Okay. So I'll go through the code and try to walk you through the what it happens. So okay. So this is the sequential layer. So if you go to Torch has a model called NN. So in NN, you have something called sequential. Okay. So by sequential, I mean, if you see my notes here, if I see my notes here, here I have, okay, so this is weird because it is not. So if you see, if you see my notes here, so here what is happening is that, okay, I'm not able to scroll now. What happened? I'll just clear everything. Got this. Okay, so if you see my notes now, so here this input is getting passed to encoder, and the encoder is fed into giving out Z, and this Z is again fed into decoder to get the image file and image. What we can see is that one in output of one layer is passing to the next layer. Here also the same thing is happening. Output of one layer is passed to the another layer. So if this kind of setting is there, we can say that the neural network is sequential in nature. That's why we have a sequential layer here. Okay, and nn.sequential sort of gives you that sequential feel. I mean, one input is getting into another. And you can see the fast. So in the encoder is defined as a linear layer and a ReLU layer, and the decoder is defined as the exact opposite. Here it is 28 plus 28, then 100. Here it is 100, 28 plus 28. So if I just draw this visually, let me drag it here. So that, yeah. So if I draw this visually, it will be like so 28 plus 28 is 784. 28 plus, so I just write 28 plus 28. Now I'm feeding this input to a Z whose dimension is 100, and this is again fed to another image whose dimension is again 28 plus 28. So while creating a network, what I will do is that nn.sequential, these are called linear layers. So I'll just put nn.linear, and in the linear, the first term is the input size. Input size is 28 cross 28. Output is 100, right? 100. And in the second, so after this, we put an activation function. So I told about activation function. We need, because since these layers are linear, we need to add some non-linearity. So we need some activation function. So we'll nn dot we'll put ReLU here, and again, so here till here we have designed. Then for decoder, we'll just put nn dot linear 100, 28 plus 28, just the opposite of this, and then we can close this bracket, and this is our model. But since we need the output from here, so that's why what we are doing is that we are doing this encoder and decoder division. So this encoder is a linear layer between 28 plus 28 and 100, and we are putting a ReLU here, and the decoder is just the opposite. I mean, this part is encoder, this entire part is decoder, and we'll always have ReLU or some other activation function. And so this is the setting. So there is a class called autoencoder, and every class is a subclass of this NN model, because whenever we are designing a in neural network, we need to override this model. And in the init itself, we need to define the architecture. Suppose so this is 28 plus 28 plus 100, and this is 100 and 28 plus 28. And after this, we are putting a activation function. And so forward is sort of defines what yeah, so forward is sort of defines how the inputs will move through the layers. So forward here gives me so I need to take the encoder, then put x here, and output x. So I'm using the same variable. So forward, like I'm putting the input to the encoder, like this one. I'm putting the input to the encoder and getting a z here. So this z is x here, okay, and this z is again passed to the decoder, and I'm getting the x. So I'll just rename it so that it will be better. Like let's call this z. So encoder is giving me z, and then I'm again passing the z to the decoder, and the decoder is giving me x hat. Let's say x hat, and I am returning the x hat. So it is x. Pass it to encoder, it is giving z. Pass it to decoder, it is giving x dash. So I guess so this is the setting, right? So this is the forward setting. So how it will back propagate? How it will back propagate using gradient descent? This will be taken care by the torch library. You don't need to worry about it. This PyTorch library will like take care of how to find the. So you just need to specify the loss. Okay, this is my loss. Minimize this. What it will do, like, okay, this is the loss, and I will take the gradient according to the loss, and I will optimize or update the weights according to the gradient of that output, and by taking that output into consideration, by taking that gradient into consideration, it will update the weights till it is converged. So I'll just run this. So once this model is done, we can just create a object of this class called net, and we can print also the net to see how this network is looking. So you see, you can see that it is the autoencoder model, where encoder is linear and late value with input feature of 784 and output feature of 100, and decoder is the exact opposite, again a linear layer where input feature is 100 and output feature is 784. So is this thing clear, like how this network is defined here?
Yes, sir, it is clear. I need to know that output future 100 is fixed, or we are just fixing it.
Here.
Yeah.
Okay, so if you want to, instead of like doing just input hidden output, you just want to do input hidden one, like input, then another layer, then hidden, then another layer, then output. Then this can also work. So I'll just also show that variation as well. Okay, but let me run everything, then come here and change thing and see how it is working. Okay, and also the like they have like also took the initial weights and kept it just because just to use it later. So okay, so this is the loss criterion, is the loss. So MAC loss, you see, you just import it from nn dot MAC loss, the mean square error loss. You put it as criterion. You need to minimize this, and optimizer is the optimize, like the 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 tool that you need to optimize this thing. So you said that, okay, sir, you have mentioned that we use only gradient descent for optimization or minimization. Optimization is basically minimization or maximization. So here it is minimization. So you can say that, okay, sir, you told that only gradient descent is used. So if gradient descent is used, then what is this? If the use of using different optimizers, you said there is no other way. So gradient descent is the only way where we can optimize this neural network. But there are certain variation of the gradient descent. Suppose one gradient descent is saying that, okay, you take the entire batch, you take the entire data set as input and try to optimize according to that. And some variation are saying that, okay, don't take the entire batch into consideration, just take a small chunk of it and optimize with respect to that. And someone saying that, okay, add momentum there to that, or someone saying that, okay, add velocity to that for better convergence. But under the hood, it is only gradient descent. You don't need to worry about it. You can just go to this optim documentation. You can find several variations of the optimization technique. One of them is SZT. There is also called Adam. There is also called RMS prop. You can also always play around with it and see with which optimization you are getting the best results. So these are all called hyperparameters. Okay, so you define these two. This is done. So this is the training code. Okay, training code, you for training, I told that you need iterations, right? So how many, so we're basically training to converge to somewhere, like we need to minimize the loss, or we need to find the optimal set of weights which minimize the loss. So for that, one way is that we stopped where the loss is minimum, or we can just fix it for a specific number of iterations. So here they have fixed it for 30 iterations. When the 30 iteration has reached, they will like uh, they will stop the training, and the batch size is 1,000. They have taken, like they will take 1,000 number of images, and they will train it. So I'll just reduce the batch size, because 1,000 they might have taken, because they might have large compute power. I don't think it will work here in my laptop, but let's say I'll take 1,000, and I'll see what is happening. And this is the training code. You just need to copy paste this. So if I can go through this code, but let's just assume that we know the training code and just start training. And I'll just start training, and uh, let's see how many time it is taking to train. I guess it will train faster. We could not find renderer. Loading reloads, could not find renderer. It is showing so. Let me see. Okay, this is just here. Okay, so this line is creating problems. And train image dot save message. Push index select. There's 0 lines. Okay. Let me create a data loader out of it, I guess. In that case, I guess it will be. Okay. Download data. Download. Create a data loader. Could not find renderer. Like I'm not getting why it is this error. Okay, I guess. Okay, the Jupyter renderer will let's see if it's not working or not. Okay, I can. So it is like I don't know, something happened. The renderer is not working. But okay, so we'll not train today. We'll train next time and see how this training time thing is going on and how testing is going on. But I can yeah, I can sure like definitely go through this one. The architecture question that you asked, can we do any changes? So suppose instead of going to the 100 directly, but I can do that. I can add 500 here, and then I can just go and add another linear layer, nm dot linear, and here from 500 I'll go to 100. Okay, so this I can do in the encoder. Since the decoder is the exact opposite of the encoder, I have to do the same thing in the decoder as well. So 102, then I have to go here and find at 500. And after this, okay, so after this, I need to also add ReLU dot ReLU. Okay, and also after this ReLU, I need to add NN dot linear, which will take me from 500 to 28 plus 28. And again, I need to, for complexity, I will add this ReLU, the completeness. So this thing is done, right? So did you see the idea here? Like what I'm doing is that I am okay. Okay, give me a minute. Uh, yes. So what we're doing is that we're sort of taking this 784 dimension. We are taking this 784 dimension. Initially, we passed it to a 100-dimensional vector. Then again, we reconstruct that 784 dimension. And from a 28 plus 28 image, we are making this. And from this, we can do a 28 cross 28 image. But when we, so this is the first thing that is given in a notebook. If you want to change that, what you can do is that take a 28 cross 28 image, then flatten it to get 784 dimensional vector, then get a 500 dimensional vector, again get a 100 dimensional vector. From here you find a 500, then go ahead and reconstruct the entire image of 784, and from it you will get back your 28 cross 28 image. So this is the same thing I did. Like I just added 500, 100, 100, 500 this, and you can see that the layers have now have changed. Like it is linear from 784 to 500, then 500 to 100, then 100 to 500, and 500 to again to 784. So it's just like going in the decreasing order and then increasing it. So what the one advantage of going deeper is that, so this is a shallow network and this is a deep network. Deep is that the representation that it will learn here, it will be much more richer than the representation that is learned here. So this Z and this Z, this will have better performance than this Z. And when we, so it is 28 cross 28. If we have say 100 cross 100 image, we need to go very deep, like 3, 4, 5 layers. Then before reconstructing it, again going bigger, 100 cross 100. So this is like intuition behind this. So did you get your answer? Like where you are asking, like, can we is this fixed or can we change it? So even if you want, like, if you want to represent the same thing using 100-dimensional vector, it is fine. If you want to represent the same thing using, let's say, 50-dimensional vector, 50, also is possible. It will be 784, 500, and 550. Then 50, 500, 500, 784. The difference is that when you reduce the number of layers in the hidden layer Z, so this will typically will allow, like, if you want to store information in 100 neurons or 100 bits, and if you want to store the same information in 50 neurons or say 50 bits, the quality of information will always be better in 100 dimension than the 50 dimension, because like 100 dimension is has more spaces and it can store the same information in a very better way. Is this clear? Could you please clarify, the person who asked this question?
Yes, sir, it is clear.
Okay. So I guess the time is going to over now. But I will definitely run all these things in the classroom itself. So I'll cover everything of week 3 and week 4 notebooks, because I saw the lectures like a bit, and I saw that it is mostly running the codes. So you should always be running the codes, and you just get the intuition and the math that is going on in the lecture, and then you just start writing code and running. So if your code is not running, so from next class you should be running codes, and so in the next live session, in the problem solving session, you just run all the codes of week 3, and let me know if you are like have any doubts, or if you want to change anything here in the codes, like the architecture and all, if you want to try out with a different optimization or different loss function that is there, or if you want to play around this, or if you have faced any problem while running the code, then I can help. So I guess so if you go to, so someone has assignment with 3 assignment a last question doubt, but I guess that person is not here now right now, or uh, who was that person who asked about the Sangeeta, I guess, with the last question, sir. But I guess he is not here. But anyway, I'll just explain that, because she can watch those videos later. With the assignment 3. And like from the next class, what I will do is that suppose week 3 videos are just released, so I'll go to week 3 and week 4. I will so I'll assume that everyone is clear till week 2. They know how this neural network works, and how these weights are optimized. And to optimize the weights, we use gradient descent. Gradient descent minimize the loss, and for coding, we just need to specify the loss. We just need to specify the gradient descent variant, and we just need to specify the network. So what the code will do, code will make a forward pass of the input, then it will calculate the loss, then it will minimize the loss using gradient descent, and after the training is done, we'll get a set of weights which will achieve our task. So according to the task, we will design the loss functions. So this is the like overall idea till week 2. From week 3, we learned about autoencoders, and we will run all the codes that is there in the week 3. Next class, also look into week 4. And okay, so week 4 is also autoencoders, and I guess denoising and all these things are there. I will cover one by one in the next class. So yeah, week 5 is all about cost function. Cost function is similar to the same as loss function. Cost, loss is same. Gradient descent learning rule, SGD, and ADAM, all these things are discussed in week 5. So let's just try to cover week 3 and week 4 by next week. And so everyone can just cooperate and try to run all the notebooks that is there in the week 3 and week 4. and let me know. At least you just run with 3. So I'll just discuss the last question in the assignment. So what will be the data loader output if we have a batch size of 1000 and batch size of 28 plus 28 of a RGB color domain? So, you must have heard that RGB has 3 channels. So the data loader that is there in the PyTorch, this one. So this one load the data from from this data set. So given a data set, it will load the data. So the data loader load in this format. The data loader load in this format. Batch size, number of channels into height into width. This is the thing. If you specify the batch size as 1000, it will be 1000. And for a RGB image, the number of channels is 3. For a grayscale image, the number of channels is 1. And height and weight is 28 plus 28. So here, if you see this question, you have a batch size of 1000. So 1000 is written first. RGB image, C is written second. So this will be the answer. But yeah, so the batch size of 28 plus 28, the image is 28 plus 28. So length cross breadth or height cross width. So this is the output. Answer A is the correct answer. So yeah, so this is the doubt cleared for question number 10 for doubts on Gita who asked, but she is not here, I guess. Yeah, so everything that I discussed today is clear, right? Or anything that need to be done or improvement, anything? You can reply in the chat if you don't like to speak up. Also, like, did you guys subscribe to the channel like that I said? So I'll be uploading all these videos there only. Or you can go to those videos and see there if you're not attending anything or you just want to recall anything. So let me go to my channel. Yeah. This is my channel. Yes. So do you guys need any other thing? So in this channel, I'll be uploading the deep learning for computer vision in uh, for every week. So apart from that, like, do you need any other content that I need to put in this YouTube channel, such that that will be helpful? Like that will be related to the course, but it will not be official video that is related to NPTEL. This will be something different, like it will be like going through the coding part or going through the sort of coding that is related to the course. Let me know. I can cover that as well and put it here. So
sir, we are having many terms in the case of deep learning. That means the topologies. For example, optimization is also equal to minimize. So like that, we are having same meaning but different words.
okay. So you just want me to like club everything and write it somewhere, right?
Yes. So like that, if you can
So,
post in your,
okay, so I'll just so you just check this channel. So the channel I said. So I'll try to make I will try to make another video and post it there itself, like terminology of deep learning, all these things.
yeah, like that. And,
or I can just write it somewhere and give it to you in the next lecture.
So whichever is convenient for you, just give, sir, no problem.
Okay. Or you can just post a question in this and I can answer that.
In the channel, sir?
Yes, not channel. Yeah, in the channel you can add in the comment section. That will be good after posting this. Or you can just post it in the forum. I can try to answer that in the forum, Swim forum.
Yeah, okay, I will do that, sir. And linear and non-linear images means what they are saying, sir?
Not images, linear and non-linear layers.
Yeah.
So linear and non-linear layers are there. So linear layer is that like you are taking the image and you are multiplying it to your weight and adding some bias. So it is like all the linear operations, right? So non-linearity is something like it will not be like it's a matrix multiplication. So what is the linear combination, or you can say linear equation that you see in the real life? Ax plus bx plus c, something like this, right? So this matrix multiplication is just linear operation. So using neural network, what you are doing is that you are approximating some complex function, and we are assuming that complex function is not linear at least. So since the target function is a complex, and you are approximating it using a neural network, and for the and the parameter of which you don't know, like you don't know the w in the neural network, right? So since you're
Okay.
approximating the complex function using neural network, and since just by adding neurons and multiplying it makes it a linear function, and since the target function cannot be linear, right? Because target function is something very complex, so you're just adding non-linearity on top of it. The ReLU layer is a non-linearity, like you are adding a linear layer which will take the input and multiply it with the weight and give the output, and add a bias, give the output. If you directly use that output, it will be linear operation of the input. But if you add a ReLU on top of it, so that will be a non-linearity. The output is passed to the ReLU, and ReLU is kind of this shape, and it will add a non-linearity on top of it. So it will help to approximate the function better.
Okay. Okay, but adding weight and giving bias, which it
It's just
promotes to
linearity.
linearity, which it promotes
Yeah.
to linearity, but
Okay. So
the ReLU.
if you remove the ReLU here, okay. So if you just remove all the ReLU layer here, it will be a linear function. Why? Because you are taking x of size 794. You're multiplying it with w. Okay, adding bias, and then you are again multiplying it with the output using w. So you're just doing a linear operation, right? So yeah.
Okay. This 500 represents the number of pixels, sir.
Which one?
This 28 cross 28,
Yes,
500.
the number of
It's
pixels.
500.
The MNIST is a 28 plus 28 dimensional image. So if you take another data set called Cipher 10, Cipher 10 is 32 cross 32. So
Yeah. No, I'm just asking this 500. 500 is again
500
pixel,
is the
right?
next, not pixel, neuron. You can say neuron. So here it is
Neuron.
pixels. Once you stretch it, like 20 plus 28 is there, you just take the first row. You just take the first row and put it here. Then second row, put it here. So you can just stretch the image into 784 dimension. Then you take this 784 dimensional vector, and you then again um, multiply it with a weight W1, say, and you get this 500. So if the input is 784, you need to multiply it with a 784 cross 500 dimensional matrix. Then it will be cancelled. It will give you 500 dimensional vector. So these are neurons. Okay. And this will again be multiplied with something else. You'll get 100 dimension and so on. These are neurons. These are inputs. They're weights.
Okay, this is new answer.
Yes, sir.
Okay. This step is known as flattening, right, sir?
This is known as flattening, yes. Like you are flattening out the image. And we will also discuss about the techniques which is called convolutional neural networks, which doesn't flatten things, because when you go to bigger images, 100 cross 100, so it will be 10,000 dimensional vector, which is very large. And the matrix that you need here is 10,000 cross something, which is very large, and it would not fit in our memory. So we'll learn about how to deal with that with bigger images. 100 cross 100 is even less. When you go to HD image, it is 1,000 cross 1,000, which is around 10 lakhs. So it when it goes like very deep. So it is not able to, we're not able to do this. So we'll learn about that technique as well. Okay.
Okay, sir. Thank you.
Okay. So I'll just stop the